What if I told you that researchers at MIT just found the cheat code to make AI actually think? And I'm not talking about boring tech jargon, I mean real, dynamic thinking. A team of researchers from MIT recently published a paper titled The Surprising Effectiveness of Test Time Training for Abstract Reasoning. What they've done is incredible. They've taught a computer to solve problems it was never trained for, and to improve itself in real time. Yes, real-time self-improvement. This is like a Q-Star 2.0 moment for the AI world. In this video, I'm going to break down exactly what test time training is and why this breakthrough could bring us closer to AGI, artificial general intelligence. Let's start with a simple example. Look at this grid puzzle. Here's the input, and here's the output. For us humans, it's pretty obvious. Just fill the blank square with yellow to complete the pattern. Easy. Right? But for a language model, this kind of test is nothing short of a nightmare. So how does test time training change the game? Stick around and I'll explain everything. Here's the thing about AI right now. It's like that one student in class who's amazing at memorization. Ask them a question they've studied before or something similar and they're like, got it! But the moment you throw them a curveball, something completely unfamiliar, they freeze. Take this thing called the ARC benchmark, for example. It's designed to test artificial general intelligence, or AGI for short. It gives AI these little puzzles that are super straightforward for humans. Stuff like, here's a pattern, what comes next? Easy, right? But for AI, not so much. Humans can score an average of 60% on this test. But until recently, the best AI models could only manage around 42%. That's a huge gap. Look at this example. For us, it's obvious, oh, just rotate the shape or fill in that square. But for AI, it's like giving a Rubik's Cube to a cat. It's completely lost. And then boom, enter test time training, or TTT, a genius breakthrough from researchers at MIT that's honestly a complete game changer. This method lets AI models adapt on the fly, learning while they're solving problems. And here's the kicker. It's not like the traditional fine-tuning that takes weeks. This happens in real time during inference. Think about what this means. We don't have to rely solely on pre-training anymore. Models can now adjust and learn by themselves as they encounter new problems. That's massive. And let's be clear, this is totally different from test time compute, which we've seen in models like O1 and O1 Mini. With test time compute, models can think longer to solve tough problems, but they don't actually train themselves while doing it. That's the critical difference between test time compute and test time training. For a second, imagine you're an AI taking a test. Normally, you just try to answer questions based on what you already know. But with TTT, it's like getting to study a few practice problems right in the middle of the exam. You figure out the pattern, adjust your approach, and then ace the question. It's like the ultimate open book test, and the results? Mind-blowing. They tested TTT on an AI model, and guess what? It went from scoring 42% on the ARC benchmark to a whopping 61.9%. That's human-level performance. And here's the crazy part. This wasn't some enormous resource-heavy model. It was just an 8 billion parameter model. Now imagine applying this to something like a Llama 400B, or another proprietary giant model. It suddenly makes sense why Sam Altman couldn't stop laughing when people claimed language models had hit a wall. The reality? AI is accelerating faster than ever. And breakthroughs like this prove we're only scratching the surface. Okay, so test time training, it sounds super complicated, but it's actually pretty simple when you break it down. Let me walk you through how this self-improving AI actually works. When this AI gets a problem, instead of just staring at it like, what now? It gets creative. The first thing it does is generate a ton of variations of the problem. For example, if it's a grid puzzle, it might rotate the grid, flip it, change the colors, you name it. The goal is to create enough examples for the AI to uncover the underlying logic. Then comes the really cool part, stage 2. The AI takes those new examples and fine-tunes itself, but only for that specific problem. And it does this super efficiently using something called LoRA, or low-rank adaptation. Instead of rewriting its entire brain, it just makes a quick, precise tweak to a tiny part of its system. Once the problem is solved, it wipes the slate clean. The AI goes back to its original state so it doesn't carry over any weird biases to the next problem. It's like using a whiteboard, write on it, solve the problem, and erase it when you're done. Genius, right? Now, you might be wondering, why is this such a big deal? Let me break it down for you. Reason number 1, it makes AI smarter on the spot. Right now, most AI is static. It knows what it knows, and that's it. But TTT, it makes AI dynamic. It can learn and adapt in real time, which is a massive leap toward making AI more human-like. Secondly, it works with smaller models. You don't need a billion-dollar supercomputer to make this work. With TTT, Smaller models can compete with the big guys. This is huge because it makes powerful AI more accessible. Think running advanced AI on your laptop instead of needing a server farm. Third reason is it's a step toward AGI. And the big one, this is a serious step toward AGI. Generalization is the holy grail of AI. And TTT shows that models don't have to memorize everything beforehand. They can learn on the fly, just like we do. Now let's see why this is paradigm shift from existing technique like chain of thought or inference timescaling. So you've probably heard of stuff like chain of thought reasoning, right? It's awesome models think step by step, following preset pathways to get to an answer. But here's the thing, it's all based on what the model already knows. It's static. Same with inference timescaling, where you throw more compute at a problem to help the model think harder. Great, but still limited because the model itself doesn't change. But in TTT approach dynamically generates problem-specific fine-tuning data, allowing immediate structural adjustment. This isn't incremental improvement. This is a fundamental reimagining of how machine learning systems can dynamically interact with novel problem spaces. And the best part? TTT can work alongside these methods. Combine it with chain of thought or voting strategies, and you've got an AI that's not just smart, it's strategic. Now let's zoom out for a second. What does this mean for the future of AI? Right now, we're kind of hitting a wall with training. We've already used most of the public data available, and creating synthetic data isn't perfect. TTT is a way to squeeze more value out of what we already have. It's not about feeding the AI more data. It's about teaching it how to think better with the data it's got. That's a game changer. This could make AI faster, cheaper, and more accessible to everyone, not just tech giants with endless budgets. Alright, so what's next? Right now, TTT is being tested on abstract reasoning tasks like ARC. But imagine applying this to other areas. Healthcare, robotics, finance. Picture an AI doctor that learns about a new disease while diagnosing it. Or a robot that figures out how to navigate a new environment on the fly. The possibilities are endless. So there you have it, test time training. It's smart, it's efficient, and it's pushing us closer to AGI. But here's what I want to know. What do you think? Is this the breakthrough we've been waiting for, or just another step along the way? Let me know in the comments.